Hello everyone and welcome to Applied Engineering channel. Here we discuss the innovative ideas and concepts regarding the thermodynamics. So this is the part 3 of the PhD defense series. So in my research phase 2, we went a little bit more deeper into the simulation, and instead of 3E analysis, we performed 4E analysis, which include the economic analysis also, because plant cost is also one of the important prospect for the refrigerant selection. And not only we enhanced our model from 3E analysis to 4E analysis, we also validated our model in the actual environment of Japan for one of the largest ultra low temperature refrigeration industry in Japan, that is tuna industry. The tuna industry of Japan has a long history of using high GWP refrigerants. At first it was using R22, but due to its ozone depletion characteristics, they shifted from R22 to R23 and R404A. Then due to the high GWP values of R23 and R404A, they shifted towards CO2 and ammonia. CO2 is a natural refrigerant with GWP value of 1 and very good thermodynamic properties. But the issue is its triple point of minus 56.6 degrees Celsius. So CO2 system cannot go beyond minus 50 degrees Celsius. Whereas the latest research regarding tuna refrigeration says that it has to be stored at or below minus 60 degrees Celsius to retain its freshness, color, and taste. For that, more than 50 air refrigeration systems were installed in South Korea and Japan, which use air as a refrigerant. But these plants comes with very huge equipment and its performance is not as per the Cascade refrigeration systems. So this research objective is to find some natural refrigerants and focusing on improving the energy efficiency and reducing the environmental impact and achieving the desirable ultra low temperature efficiently. In the second research phase, we selected the best low temperature refrigerants from our first phase study, that is R41, R170 and R1132A. R23 and R404A are again used as a baseline. And for the high temperature cycle, for the first time we introduced cyclobutene, cyclopropane, butene, isobutene, cisbutene, transbutene, and 1,3-butadiene. This Venn diagram summarizes the refrigerant selection used for the cascade refrigeration system, where the set is representing the LTC refrigerant like R23, and inside the set you can see the high temperature cycle refrigerants which are used with that. So these natural refrigerants you can see were used for the first time in this study and they were never being used before. Following figure shows the process flow for the 4E analysis. We performed similar thermodynamic and environmental analysis as before. Additionally, we modified it to calculate the hourly data to evaluate the exact energy consumption COP Exergy efficiency by using the Japan hourly weather data. Secondly, we utilized that hourly annual energy consumption data to evaluate the total indirect emission as well as the operational cost rate in the economic model. Also, to calculate the total environmental cost, we utilize the LCCP emission data. So this interlinkage of different models was implemented for the first time and it resulted in very insightful results. Figure 24 shows the Japan map showcasing different low and ultra low temperature cold storage houses with the red mark. The yellow stars shows the selected location for the 4E analysis, which are selected based on the extensive number of low temperature cold storage sites. Japan has very diverse climatic conditions from Hokkaido to Okinawa, and Table 8 summarizes the latitude and climatic parameters showing an inverse relationship between the temperature and the latitude. Based on this data from the Japan Meteorological Agency, Japan can be classified into three climatic zones. Zone 1 is Sapporo and Sendai, severe cold to mild climates. Zone 2 is Tokyo and Nagoya, which has mild to warm climates. And Zone 3 has Shizuoka, Osaka, Hiroshima, and Fukuoka, which has mild to hot climates. Furthermore, figure 25 shows that the 10 years average annual ambient temperature bin data, further verifying the varying climatic condition in these 8 cities. By utilizing the following cooling load equation, which was established for low temperature systems by an experimental study based on 20 kilowatt design cooling load, we calculated the hourly cooling load for the 8 cities of Japan using average hourly 10 years ambient temperature data. The figure shows the monthly cooling load and the average monthly ambient temperature data. The trend of cooling load is quite obvious as it increases in the peak summer season, July to August, and reduces in the peak winter season, that is December to February. The economic model consists of total capital and maintenance cost rate, operational cost rate, and the penalty cost rate due to CO2 emission. The cost function of the system components are evaluated using these correlations. The total capital investment and maintenance cost rate is the sum of all these cost functions by multiplying with the interest rate and maintenance factor. The total operational cost is evaluated using this equation, which is annual operational hours multiplied by the total compressor and fans work multiplied by the commercial electric power cost in Japan. The total environmental or penalty cost rate is evaluated using this equation, which includes the LCCP divided by the number of years multiplied by the penalty cost of CO2. The following model is validated with the Roy and Mundell model, and you can see that the deviations are less than 8%. So this model is validated and it can be utilized to calculate or to do economic analysis. The COP and Exergy efficiency of the refrigerant used in this study were compared to the three most cited studies in this field. In this figure, you can see that the result comparison with the first study of Roy and Mundell. As compared to this study, the present study has 7 pairs that outperform its highest performance pair, and we can have a maximum of 3.7% higher COP and 3.1% higher Exergy efficiency. So here is the graph representing COP on your left side with a pink color and Exergy efficiency inside these bars with a brown color. This comparison was done under the similar conditions as of the reference study. Similarly, this is the second most cited study of Akhtamar. And you can see that the 7 pairs of the present study outperforms and 4 pairs match the highest reference study pair. A maximum improvement of 4.1% in the COP and 4% in the Exergy efficiency was observed. Similarly, this is the third most cited study of Sun. As compared to this study, the present study outperforms 9 pairs and 3 pairs match the highest reference study, and a maximum of 3.2% higher COP and 3.4% higher Exergy efficiency was observed. These results assured that the present refrigerant pairs outperform all previous records and has the highest COP and the Exergy performance values. These are the plots of energy consumption throughout the year of 8 Japanese cities with selected high performance HTC refrigerant cyclobutene, and R23 and R404A is baseline. R170, R41 and R1132A are the prospective refrigerants. The first thing we can observe that R23 pair is consuming highest energy consumption as compared to all prospective refrigerant. Here the blue points represents R23 and the green points are representing R41 and the yellow points in between are representing R1132A, whereas the pink points are representing R170. The other y-axis is giving us the cooling load plot. Another important thing which we can observe is that the high temperature zone cities, so the high temperature zone cities have more difference of this energy consumption as compared to the low temperature zone cities with respect to baseline, and you can see the points are becoming wider. So R170 and cyclobutene consistently has the lowest energy consumption across all the cities, whereas R41 cyclobutane has improved energy efficiency over R1132A in hot climates and R1132A has improved energy efficiency over R41 in cold climates. So for this we can say that we have to select climate specific refrigerant for minimizing energy consumption and indirect emission. So this is the plot of annual energy consumption. Here we can see on the primary y-axis is the total energy consumption throughout the year of the 8 Japanese cities with different refrigerants. And on the secondary y-axis we can see the annual energy reduction of R170 as compared to baseline pair. So the key points or key observations were we have the highest energy consumption in Fukuoka of 164.72 megawatt hour and the lowest energy consumption in Sapporo with 130.25 megawatt hour. And for the energy reduction, we see that with R170 as compared to the baseline pair, we have an energy reduction of about 8.1% in Fukuoka and 6.48% in Sapporo. So we can say that cities with higher ambient temperatures show greater benefits from R170 and cyclobutane pair. These are the plots of COP of the 8 cities of Japan along with the ambient temperature. Here we analyze the hourly COP variation with ambient temperature. So the key trend was COP inversely correlates with the energy consumption and the refrigerant pair performance was similar to the energy consumption. The highest COP was observed in Sapporo whereas the lowest COP was observed in Nagoya. These are the plots of exergy efficiency along with ambient temperature throughout the year of the 8 Japanese cities. The key trend observed in that the prospective pair exergy efficiency increases with the ambient temperature, whereas for the baseline R23 and R404A it declines in the peak summer. Although energy consumption and COP show similar trends with the temperature, but the exergy efficiency trends differ because it captures the quality of energy, environmental effects, and irreversibility across all the system components. Some refrigerant pairs like R170 handle high temperature better, showing reduced entropy generation leading to improved exergy efficiency in summer. Meanwhile, R23 and R404A shows increased irreversibility at higher temperatures and hence decreasing the exergy efficiency. The following plot illustrates the total LCCP in tons of CO2 and the percentage emission reduction for the selected refrigerant pairs across the various Japanese cities. It is evident that the baseline pair R23 and R404A exhibits the highest total emission compared to all prospective refrigerant combinations. It is due to its high direct emission driven by the high GWP values of the refrigerant. In contrast, the prospective pairs shows a negligible direct emission. R23 and R404 pair combination also records the highest indirect emission among all the refrigerant pairs. Here we can see the emission reduction results of R170 as compared to R23 and R404A. For the Sapporo, we have the highest LCCP emission reduction with 47.46%, whereas for Fukuoka, we have the lowest CO2 reduction with 44.63%. So this implies that R170 and cyclobutane is the most environmentally efficient pair, minimizing the LCCP emission. This plot shows the economic analysis showing the total cost rate and the annual cost reductions. As already explained that the total cost rate is the sum of capital cost rate, operational cost rate and environmental penalty cost rate. The key findings are that R23 and R404A has the highest total cost rate, whereas R170 and cyclobutane has the lowest total cost rate. But when we divide or break down the total cost rate into capital and maintenance cost rate, operational cost rate, and environmental penalty cost rate, we see that R1132A has the minimum capital and maintenance cost rate, whereas R170 and cyclobutane pair has the minimum operational and environmental penalty cost rates. So R1132A reduces the capital and maintenance cost as compared to R23 R404A by 11%, whereas R170 and cyclobutane reduces the operational cost as compared to baseline with 6 to 8% and the environmental cost by 44 to 47%. The overall annual cost reduction by switching from R23 to R170 is 18.78%. So the key findings for the research phase 2 is that all the alternative pairs outperform the baseline R23 and R404A, and the COP is improved from 3 to 15% as per the temperature, and the Exergy efficiency is improved from 3 to 12%. Annual energy consumption saving was up to 8% annually in high demand cities. The environmental impact lowers by 44 to 47% as compared to the baseline, and it reduces the total cost as an average of 18.78% across all cities. So in this second research phase, I had again two publications, one in the energy and another in the gesture conference. In the next video, I will share my third phase of research. If you have any question, please ask in the comment box. I would love to answer your questions. Please like, share and subscribe my channel if you like more videos and updates. That is only way of supporting and motivating me. Thank you very much.